So in this video, we're going to talk about three different types of collisions. We're going to talk about inelastic, elastic, and completely inelastic collisions. So yeah, let's just get into it. We'll start off by giving an example. Let's say we have a mass here. We have a mass here. And maybe originally this mass was moving at v1, and then this mass hits into this mass. This mass is going to hit into this mass. So then they stick together and they both travel at some new velocity. So let's calculate this velocity, what this velocity is in terms of m1, v1, and m2. Okay, so our original momentum is equal to m1, v1, there's no momentum contributed here, and our final momentum is equal to m1 plus m2 times v1 comma 2 prime, right? And now we just set these equal because momentum is conserved in any collisions, and we say v1 comma 2, right? So I say this is equal to this, so I can divide this over here is equal to m1 v1 over m1 plus m2. Alright, yeah, so that was easy, but now let's say I also wanted to find the energies in the system. So let's calculate the original energy here. Kinetic energy is 1/2 mv squared, so 1/2 m1 v1 squared. This contributes no kinetic energy because the velocity is 0, right? And then our final kinetic energy is equal to 1/2 the total mass, which is m1 plus m2 v squared. So this is the velocity, but we can also write it as this, so we'll square this instead. So that's m1 v1 over m1 plus m2 squared. If I just do a bit of rearranging, right, m1 plus m2 squared, m1 plus m2 over m1 plus m2 squared is just 1 over m1 plus m2. I can actually just write this as 1/2 m1 v1 squared times m1 over m1 plus m2. I'll leave it to the reader to verify this. But you'll notice these two are very similar. However, this has this fraction here, right? This stuff is the same, but now we have this fraction. Well, masses are always going to be positive things, right? We can't have zero mass, or else we just say there was nothing there in the first place, and we can't have negative mass because that just doesn't make sense. So this fraction is going to be less than 1. Since this fraction is less than 1, what does that mean? That means that this thing is less than this thing, right? Because this energy is going to be less than this energy. Okay, but why? Why is this energy less than this energy? Well, first, I'm going to classify this collision as a completely inelastic collision. And completely inelastic collisions, completely inelastic CIC, completely inelastic collision are going to have multiple objects, maybe like two, and they move. They both maybe have an initial momentum, but then in the final state, they turn into one object that moves at some momentum, or moves at some velocity, right? So multiple objects stick together. And we found that we lose energy in this case. But in fact, for any completely inelastic collision, we're going to lose energy. The reason is, let's say we have like two pieces of clay, right? If two pieces of clay stick together, well, then the two pieces have to compress, right? If I had one moving this way and one moving like this, then for this to stick together, this one is going to hit into this one, and it's going to lose its momentum, or it's going to lose its velocity, right? Some of its velocity to stick to this one. So it changes its velocity to stick to this one, and right, it compresses, it squishes into it, this one squishes into that, and that compression creates heat. So energy is lost. It's converted from kinetic energy into heat. Another example might be like, let's say we have a block and a bullet. We shoot the block, and the bullet gets lodged in the block, and they move together. Well, the bullet is going to, the only reason it gets lodged in the block is because friction stops it from passing through the block. Friction, right? That means work is done by friction. So that generates heat. Again, we lose energy. Completely inelastic collisions, we're always going to lose energy. Alright, I think it's also a good time to talk about something called explosions. It's not exactly a type of collision, but it's basically where you go from one object and you split it into multiple different objects. And with explosions, again, momentum is conserved, but even though momentum is conserved, we still have, or we are going to end up with more energy than we started with. Like, it takes energy for me to break apart an object, and that's where this extra energy comes from. The energy it takes to break apart the object is like an applied force. Maybe we have like a chemical reaction that causes it to explode, or maybe we have like a lever that pushes it, or we unlock a spring. It takes energy to unlock that spring, so we add more energy into this system. Yep. And then we get to elastic collisions. Elastic collisions are going to preserve energy. Kinetic energy is going to be preserved. We're going to have that conservation of energy. So, elastic collisions are generally going to have one object. They're going to have one or some objects, right? And then when they bounce into each other, they bounce back. They bounce back the other way. The velocities are could change, right? The velocities can change because maybe a heavier one hits a smaller one. The smaller one is going to go faster. The heavy one is going to go slower, things like that. But energy is conserved, and that's just the most important part about elastic collisions. Yeah, so elastic collisions, energy is preserved. Anything that doesn't preserve energy, that's not an explosion, is going to be an inelastic collision. So maybe we don't preserve energy, but the objects don't stick together. Like maybe we have a thing here. They crash into each other, they squish a bit, but then they bounce back a tiny bit. If we, at any point, we lose energy, it is going to be an inelastic collision. If we gain energy, it's most likely an explosion that happened. All right, so we can actually find some interesting things about elastic collisions. So with elastic collisions, our initial momentum is equal to our final momentum. What does that mean? Well, let's say we had started with, let's just say we had two objects, right? M1, V1 plus M2, V2 is our initial, and our final momentum is M1, V1 prime plus M2, V2 prime. What about the kinetic energies? Well, the kinetic energies are 1/2 M1 V1 squared plus 1/2 M2 V2 squared, and this is equal to 1/2 M1 V1 prime squared plus 1/2 M2 V2 prime squared. I'm going to move this onto this side and this onto this side, right? So this goes here, so I combine all the 1s and 2s together. So I get 1/2 M1 V1 squared minus, oh, and I'm going to multiply everything by 2, because it's an equation, so I can do that. And minus M1 V1 prime squared is equal to M2 V2 squared minus M2 V2 prime squared. Alright? I'm actually going to do the same thing here. So I'm going to rearrange it so it is M1, M1, oh, and I can also factor out the M1, right? So I can factor into M1 V1 squared minus V1 prime squared is M2 V2 squared minus V2 prime squared. Here I do the same thing and I change this to V1 minus V1 prime, right? I move this here and this here is equal to, or I move this, this goes over here and this goes over here. Oops, okay, there's fixed. Is equal to M2 V2 prime minus V2. Okay. So this negative, I should have had a negative here because when I moved it around, right, this side would be negative, right, because I moved this over here, so that's negative, and this is positive, so this negative factors into here, and I can instead flip the things, or flip the order of the square, and it becomes this. Now, I'm going to divide this equation, or this equation, by this equation, and what do I get? Well, on this side, the m1's cancel, and by some algebraic rules, we know v1 squared minus v1 prime squared divided by v1 minus v1 prime is equal to v1 plus v1 prime. And on this side, right, we get v2 plus v2, similarly, v2 prime. So, we just found our initial velocity for object 1 plus its final velocity is going to equal the initial velocity of object 2 plus its final velocity. So that's interesting and all. But there's actually one more thing that's more important. So we want to solve for something else. This thing is a bit difficult to solve for, so I'll just outline how you can do it and leave it as an exercise to you to do it. So what you want to do is you want to say, okay, let's say I know that let's say I want to solve for v2 prime in relation to v1, v2, m1, and m2. Well, then I can just plug in to the v1 part, v2 plus v2 prime minus v1, right? All I did was rearrange. I plugged this into the v1, so now I have things that are just v2, v2 prime, and v1. And then I can rearrange the equation so I have v2 isolated on one side, and then the rest of the stuff, v1, v2, m1, and m2 are on the right side. And when I rearrange, it's going to give something that looks like this. So I'll write down the first equation that was important. Right? So the first thing that was important is that v1 plus v1 prime is equal to v2 plus v2 prime. But the second thing is when we rearrange, we can solve that v2 prime is equal to m2 minus m1 over m1 plus m2 multiplied by v2 original plus 2m1 divided by m1 plus m2 multiplied by v1. Alright, and then similarly, if we just replace the coefficients 1 and 2 and rearrange, we get v1 prime is equal to m1 minus m2 over m1 plus m2 times v1, the original v1, plus 2m2 over m1 plus m2 v2. Yeah, so there we go. These equations are important. And we can actually see them in action. So one of the coolest things to see with these equations is, let's say that we have a ball of some mass m. So let's say the masses are equal. And then this ball is going to move, and it is going to bounce into this ball of the same mass. So let's say this is ball 1, v1, and this is ball 2. Right? I want to find, and this is v. v1, right? Because it's the velocity of ball 1. The original velocity of ball 2 is 0. So I'll say v2 equals 0. Alright, so if I want to find the final velocity of ball 1, I plug it into this equation. Well, m1 is equal to m2, so this part is 0. But, and v2 is equal to 0, so this whole thing is 0. Okay? So that means this ball is going to, once it hits this ball, it's going to go stationary. What about this ball? Well, if I plug it in, this part is 0, but this part turns into 2m over m1 plus, or m plus m, because m1 is equal to m2 is equal to m. So I get 2m over m, which is 1, times v1. So this ball is now going to move, this ball is now going to start to move at v1. So what does that mean? Like, if I have, that means if I have two, oh, this is stuck together. Let's say I have like two balls, right? And they're of the same mass. When I move this one moves at some momentum, the momentum transfers over. And you can see that with billiard balls, right? If you start hit one of them at some velocity, like the white ball, and it hits into another ball, the white ball will stop and the other ball will move, assuming it's a kinetic collision. So that is something cool. All right. So with that, we wrap up the unit, and yeah, there we go, conservation of momentum. Awesome. All right. So see you